So up until now, we've only been considering stars as individuals. Now we want to study their surroundings and how they are formed and how they group together. Space is nowhere truly empty. We find thin gas filling the space between stars, plus dense patches which we see as nebula. This is a picture of the Horsehead Nebula. We also see the M16 cores, or the gaseous pillars, as we have dark material filling up the space between us and the stars in the background. So, the interstellar matter, why is it important? Well, it's the substance out of which new stars formed, and it also hides and distorts what lies behind it. There are two components of interstellar matter, gas and dust. They go together, but sometimes one is more visible than the other. The gas is about 75% hydrogen, 25% helium, and less than 1% other stuff, basically like the sun. It may be ionized, as in the bright nebula, or it may be neutral or molecular. Hot thin gas tends to be ionized. Cool dense gas tends to be neutral. In interstellar space, the density is something like 1 atom per cubic centimeter. Nebula may be 1,000 times thicker than this, but either of these is much less dense than the very best laboratory vacuum we could ever get. The dust is particles of minerals and ice grains. We don't have much direct knowledge of what the dust particles are made of. They're very tiny. They're like individual grains of smoke rather than sand grains. About 1% of the mass of interstellar matter is dust grains. It also represents a large fraction of some elements in our galaxy. So how do we observe the dust? Well, through reddening and extinction. Dust absorbs and scatters light, so that a star is dimmed if there is dust in front of it. And that dimming is called extinction. Thick clouds containing dust can make background stars invisible. We call that a dark nebula. Here we look at this field of stars and we see this area here where it looks like there's fewer stars. It's not that there's fewer stars there. It's there's a cloud of dust in between us and the background stars that hides the stars behind it. If the dust cloud is not too thick, the light will only be partly dimmed. Blue light is absorbed and scattered more than red light, so a star with dust in front of it looks redder than its natural color. This is a limitation on the use of Wien's law for determining solar temperatures. As the light from this yellow star goes through the cloud of gas and dust, the blue light is scattered and only the red light, and so the star looks red to us on Earth. This same effect causes the sun to appear red at sunset. The effect is stronger at sunset because the light has to pass through more atmosphere when the sun is near the horizon. So some of the light is reflected. That means that dust close to a bright star can scatter light. The bright patch is seen as a reflection nebula. Essentially a star gives off light, and as it goes through the dust, light goes through the dust cloud here, the blue light is scattered and it goes in all directions, some of which goes to us, and we look like a blue nebula. The Pleiades are an example of this. They are a set of relatively young stars. They're in a lot of dust from the clouds that they were formed out of, and the dust looks blue from the scattering of the blue light from these stars. Now there's many examples of these type of nebula where you get a dust cloud where the blue light is scattered from it. When light is absorbed, the energy goes into the dust grain and it heats up. The temperature is perhaps 10 to 50 degrees Kelvin, which is very cold by Earth standards, but enough to produce strong infrared emission. Infrared emission is also useful because it is scattered and absorbed even less than red light. One can thus penetrate deep into clouds by this method. This looking at IR is particularly useful in the study of newly forming stars. Now, here we have an infrared image of the whole Milky Way. Notice how the appearance in the visible down here is strongly affected by extinction. If we look at our Milky Way, we see patches that it looks like it's empty. But if we look at different bands in the IR, we see, no, the galaxy as thin. We have the nuclear bulge we'll talk about later. In other bands we can see a lot more of the Milky Way galaxy and see it's a solid band than we can in the visible light. So nebula. The hot stars, the O and B types, give off so much ultraviolet radiation that they ionize the surrounding gas. The temperature can get up to 10,000 degrees Kelvin. The gas in a nebula is often the remnants of the gas cloud out of which the star is formed. These are pictures of nebula, where the hot stars inside of them are causing heating of the gas and dust around it and causing them to emit in different wavelengths. These nebula can be very beautiful. This is the Boomerang Nebula. Now, much of the diffuse gas is neutral atoms with a density of about 1,000th to 10 particles per cubic centimeter. And we can observe them two main ways: diffuse absorption lines and 21 centimeter lines, which would be in the radio part of the spectrum. Now, a few elements have absorption lines in the visible, although more often they're in the ultraviolet. The lines appear in the spectra of stars, but are different from the stellar lines in that they are very narrow because the low temperature makes for small Doppler shifts. So the interstellar lines are very sharp in between all these stars that are all close together. The stellar lines might be more diffuse. So we can see then which ones are the lines from the material between us and these group of stars. And radio waves are completely unaffected by dust, so that they travel all across the galaxy. So by studying the 21 centimeter radio lines, we're able to map out our galaxy in much better detail. Hydrogen atoms emit a strong spectral line at the wavelength of 21 centimeters. We can thus map out the whole galaxy by studying the radio emission from this line. You can also measure the redshift of the line so that you know how the gas is moving. In dense regions, more than about 10,000 particles per cubic centimeter, gas atoms hit each other so much that they start to join together and form molecules. These have spectral lines in the millimeter and submillimeter region of the spectrum. So if I look at a spectrogram and I see all these absorption lines, I see all these different organic molecules. Now, many organic molecules have been found in these type of clouds. These clouds are often dark and cold, often only a few degrees above absolute zero. As we're going to see in the next section, these are the places where new stars form. So where do new stars form? Stars form out of interstellar clouds. One way we know this is that O-stars, which have the shortest main sequence lifetimes, are often found next to interstellar clouds. The main condition for the formation of stars is that gravity overcomes pressure. For gravity to be strong, we want to have a lot of matter in a small space, a high density. For pressure to be low, we need a low temperature. It can be shown that for any particular cloud, there's a critical density. If the density is high enough, the cloud will collapse. But if it's not high enough, it'll tend to expand or stay roughly constant density. Sometimes a cloud can be squeezed to a high enough density to collapse by an external force, such as shock waves from a nearby supernova explosion. Therefore, the place for stars to be born is cold, dense gas clouds. The gas we see as nebula, hot and bright, is not going to make new stars. It's the dark patches we sometimes see in front of the nebula that will form new stars. So in this nebula, we see several areas of dark patches. It's in these dark patches, these cool, dense clouds, that new stars are most likely to form. The gaseous pillars inside are often called stellar nurseries, and we see new stars being born inside these pillars. We call these stars protostars. A star forms as matter falls towards the center of an unstable cloud. The center heats up as the inward motion gets turned into heat motions. The protostar is initially visible only in the infrared. The dust surrounding the newly formed star radiates heat and looks like a cool object. For a while during the formation of the star, it can become even more luminous than its main sequence luminosity. So low temperature leads to too low of a pressure to support a cloud against gravitational collapse. Collapse can be triggered, again, by collision with another cloud, a star explosion, or some other process. Non-uniformity, or the clumpy nature of gases, lead to formation of smaller, warmer, and denser clumps. So rotating dense clumps flatten into a disk. About 1 million years, a small, hot, dense core at the center of the disk forms a protostar. Now, stars generally form in groups of similar age. The characteristics of a protostar is its temperature is about 1500 degrees Kelvin. They shine at infrared and radio wavelengths. Low temperature and obscuring dusk prevents visible detection. And they may be found in something called Bok globules, or dark blobs 0.2 to 2 light years across, with masses of up to 200 solar masses. Gravity continues to draw the material inward. Eventually, protostars heat up to about 7 million degrees Kelvin in the core, and between 7 and 10 million degrees, hydrogen fusion commences. At that point, the collapse of the core ceases, but the protostar continues to acquire material from the disk for about another 1 million years. The infalling material creates violent changes in brightness and ultimately a strong outflow of gas. So if I look at a protostar forming on an HR diagram, a young protostar will be very cold, and as it starts to collapse down, its brightness can get actually really bright. Eventually, though, it'll come down and find its place on the main sequence, where it will remain until hydrogen burning ceases. Now, the more mass you have in an area, the more gravity, the quicker this process happens. So a 15 solar mass star might only take 160,000 years to go through the protostar stage. A 1 solar mass star, like our Sun, took 30 million years for this collapsing gas cloud to form a star, where a half solar mass might take up to 100 million years to collapse down to become a star. Eventually, the outer cloud dissipates, leaving a star that's more luminous than a main sequence star. The last stages of star formation involve the star fading slightly and reaching the main sequence. The Sun took 30 million years to do this, and O-star takes only 160,000 years. Now, as the cloud rotates, it spins out into a disk. This is how planets were formed. A second feature of the rotation is that it apparently leads to jets of material being blown out from the poles of a spinning protostar. We call these Herbig-Haro objects. They're large, long, thin jets of material that squirt out from a young star, carving a cavity in the gas around the star, creating bright blobs, Herbig-Haro objects, when the jet hits the surrounding gas. We don't know exactly how these work, but the best theory so far is that magnetic fields in the disks surrounding the new star focus the matter into jets.